Hello again. Let's go ahead and continue on with a lecture on implicit differentiation. We're actually going to start with a little bit of recall on derivative notation. So we've seen this beginning stuff before, but let's go ahead and recall it because it's going to be important for what we'll be talking about here. So derivative notation. So if I have a function y equals f of x. So we might identify that function as just, hey, y. We might use function notation and say f of x. But if that's our function, we can write the derivative in a handful of ways. Probably the most common is just writing f prime of x. We could also write y prime of x. That'd be fine. A little shorthand for y prime of x would be just writing y prime. And then we've also seen this notation with the d dx in there and dy dx. We've seen another one that's not really that important here, but d dx of y. That's kind of similar to here, so I don't really bother emphasizing that, so that's okay. But really, we've got these handful of ways that we can write the derivative of a function. Like I said, the most common being f prime, but today we're really going to be looking at these two right here, y prime and dy dx. And the reason that these are useful will be pretty evident. But in this case, it just tells us that, hey, like dy dx in particular, this is the derivative of y. Whatever y happens to be, whatever the function is, I don't know what the function is necessarily. It could be anything. It could be x squared. It could be e to the x. It could be a ln of x. It could be anything like that. But whatever that function is, my derivative is notated by dy dx. So what I want us to think about and keep this in the back of our minds for the rest of this lecture really is to do this. This is sort of a command, if you will. Pretend that y. So when you see y written down, is really just an ugly function of x. And so what I'm getting at here is basically like think to yourself that when I say y, replace it with, I don't know, x squared plus ln of 1 over square root of x, just something really ugly like that. Or just think of it as y being equal to, I don't know, e to the x plus square root of the ln of x, just something really complicated and ugly. And the reason that I'm having us do this is because really what I want to make clear is that for the rest of this lecture, when I'm writing y, it's really just a placeholder for whatever my function is. So if my function looks like this, or it looks like this, if my function is complicated and ugly, it's just a lot easier to write y right there. So try to keep this in the back of your mind. Just pretend that when I'm writing a y, it's really just like, it's just a function. But instead of writing out that entire function, I'm just writing the letter y because that's just shorthand for it. So we've got this function y, which again, we could write it in terms of x's, but it's ugly. I don't want to. It's shorter just to write y. So I've got this function of y, and let's say that I give us y squared. And I say, hey, take a derivative of that. Well, what we can actually do is we can actually take a derivative using our normal derivative rules, but we have to be careful here. Like I said, think about this y that's in here, not the squared, but think about the y just being a function of x. So instead of writing y squared, I don't know, I could write something like, I could write x plus 3 squared. That's kind of what I'm getting at. Or maybe it's not, maybe y isn't equal to x plus 3. Maybe y is equal to e to the x plus 1, and then I'm squaring it. And there's a whole lot of, there's an infinite number of possibilities there, but just pretend that this y squared is really just a whole bunch of stuff in terms of x squared. So if I take a derivative, what I can do here is I can take a derivative of y squared. So you notice I'll say d dx of y squared. And when I do this, I am just going to do the normal old power rule. 2, drop it down. So I have that 2 in the front. I subtract 1 off of that power, giving me a y to the power of 1 here. But here's where I've got to be careful. The derivative does not just stop right here at 2y. And the reason for that is because, like we've said, this y in here is really a function of x. And so because this is a function of x, I really have an inner function here as well as an outer function out here. And so because I have that inner outer function deal, I have to use the chain rule, which says that I have to multiply this by the derivative of whatever the inner function is, which in this case is just y right there. So let me do this. I want to copy this first line right here, and put it on a fresh page just so I can sort of do an analogy here. So let's go ahead. Let's say, so this is the line that I just did. This is that step. But let's say that I had us do a different problem, and I said, let's take a derivative of x plus x squared plus 6x plus 4 squared. And I had us take a derivative there. Well, what you'll notice here, what I'm going to do is I'm going to take, and actually let's do this. So I've got that. The setup here is the same. I've got d dx of, up here I just have y squared, but you'll notice here I'm actually saying, hey, I've got this inner function. I've got this x squared plus 6x plus 4 squared. And so the setup is the same. When I do this derivative in the blue here, I'm going to do the power rule. I'm going to drop that 2 down. I'm going to subtract 1 from that exponent, just giving me, to the power of 1, which we don't have to bother writing. But then I have to use the chain rule. This is a perfect example here where we're just used to saying, hey, there's an inner function that's the x squared plus 6x plus 4, and there's the outer function that's me actually squaring that. And so I have to go ahead and I have to do the chain rule there. Well, all I'm getting at in this work that I did on the prior page here, actually, I don't even need to write any of that. All I'm getting at about this work is that it looks exactly like this work down here. It's just that up here, I don't know, I'm not stating specifically what y is. Here, I'm specifically stating that y is equal to x squared plus 6x plus 4. And so it's very easy to see, hey, drop the 2, subtract 1, chain rule that. But here, it's the same thing. It's just that instead of writing out, hey, x squared plus 6x plus 4, I'm just going shorthand. I'm just writing y. So, I've got y equals x squared plus 6x plus 4. But instead of writing that all down here, I'm just writing y right there. So then I do my 2 times y, 2 times y. This is y right there. That's y right there. And then times d dx of y. So you notice all of these underlined parts are y right there. They're all y. And this ends up looking exactly the same. And so that's kind of what I'm getting at here. On this work back here, it's just saying, hey, if I take a derivative of y squared, because y is actually a function of x, I have to do the chain rule on it. And so I do my 2y times the derivative of the inner function, which is just y. This part right here, I can clean it up a little bit notationally and just write dy dx. This is a perfectly acceptable answer, as is this. Instead of dy dx, I might just write y prime. It's a little bit shorter, a little bit faster to write. Maybe it looks a little bit cleaner. It doesn't look like there's all these fractions. So I personally would probably write that. I'd be fine with this as well, but this is our answer here. And what you'll notice is that the derivative of y squared, it is in fact 2 times y times whatever the derivative of y is. That's exactly what we saw here. The derivative of y squared is equal to 2 times y times whatever the derivative of y ends up being, which, obviously we could write as y prime right there. So this is implicit differentiation. This is the idea that we're taking a derivative of this function y without explicitly writing out what y actually is. And that's why we call it implicit differentiation, because we're not explicitly stating what y is as a function of x. And we're still getting an answer for the derivative out. So let's go ahead and look at an example of this. So let's say I gave us a function here, x squared plus y cubed equals 6x. What I'll mention is that you could start off and you could solve this for y. When I look at that, I don't want to take a derivative of this. That just looks hard. That looks like I got to do a weird power rule. I've got to do chain rule. There's a whole lot of work I have to do right there. And I don't, plus I've done this work already to solve for it. And I don't want to do all that. That's a lot of work. So what we can utilize is this idea of implicit differentiation instead. And what we're doing here in this implicit differentiation is we're going to take this equation, we're going to take a derivative of both sides. And so when I take a derivative of both sides, the x squared is going to become a 2x. And then I'm adding to that y cubed. And now we're taking the derivative of y cubed. But remember, keep in the back of your mind that y is actually just a whole bunch of ugly x's that are, all of this right here, you could even sort of just blot it out and just pretend it's a whole bunch of x's. And so since it's a whole bunch of x's, we do our normal power rule, 3y squared. But then we have to multiply by the derivative of y. And this term right here is my chain rule term. And so again, just to really emphasize this, we could be writing, instead of y cubed, I could write e to the 3x plus 4 times x squared cubed. Well, if I take a derivative of that, then that's going to give me 3 times all of this junk inside the parentheses squared. So you notice I'm just doing the power rule here. I'm dropping this 3 down and then I'm subtracting 1. So I get that 3 that drops down here, and then I've subtracted 1 to get my 2. And then I have to multiply by the derivative of all of that ugly stuff on the inside. And what I'm finishing writing here in the red is exactly what I wrote up here in the blue. It's 3 times y squared, and down here you see y squared, times y prime, which is the derivative of y. And so this in the blue, it's just shorthand for what I've written in the red. And it's just a way for me to take that derivative without actually explicitly knowing what y is. And then lastly, we get this derivative of 6x is just 6. At this point now, the goal is to find the derivative of this equation, right? Well, look right here. That's the derivative. That's y prime. That's my derivative. So if I solve for that, then I'm done. So we'll end up with 3y squared times y prime is equal to 6 minus 2x. So y prime is in fact 6 minus 2x over 3y squared. And that is a perfectly acceptable answer for y prime right there that we've found. And yeah, so there we go. We've got an answer right there for y prime. And you'll notice here that we didn't actually have to solve for y. We got it when we got an answer for our derivative. What I will note is that you could do this the long way. So you could very well do this as, hey, y cubed equals 6x minus x squared. Y is equal to the cube root of 6x minus x squared. And if you actually take a derivative of this, I'm going to do this very quickly in my head, but you're going to get, let's see, we're going to have a 1/3. We're going to have a 1/3 times 6x minus x squared to the 2/3 all over 6 minus 2x. And what I hope that you can notice here is that this looks like 6 minus 2x over 3 times y squared. And now this is a little tough, but this part right here is equal to y squared. And actually we don't need We don't need that right there. So might be a little tough to see, but this right here, this 6x minus x squared to the 2/3, well, if I take this y right here and I square it, that gives me exactly that right there. And so this term right here is y squared. And look, this orange right here, it's exactly what we found right here. But this work right here was a lot quicker than having to do all of this. And obviously, I jumped right here. I did this derivative just in my head, just very quickly. You'd probably have to show a lot more work to actually get to that step. And so there's a whole lot of steps in here that I'm not even showing that you'd have to do. It's just a lot more work than just this right here. And so this idea of implicit differentiation that I'm doing right here, it's a super quick way of taking this equation and taking a derivative. You just have to remember that y prime needs to appear there when you take a derivative that involves that chain rule term. So there we go. We've got that right there. That's our answer right there. You may be asking, I hope this example shows it well, but you might still be asking, why would I even bother doing this? I clearly can just do it this way right here. So why not? Why bother to teach this? Why not just do this every time? Why not just explicitly solve? And sure, this is an ugly derivative, but we know how to do it. So why implicit differentiation? Well, this example is a good one. It's faster. That's one way to do it, but or that's one answer to that question. But really, there's a handful of cases that we like to use implicit differentiation for. The first is that if it's impossible to solve that equation for y, in some cases, I could give you an equation that you actually just can't solve for y. And so you can't go through that method of, hey, solve it for y, then take a normal derivative. Because if it's impossible to solve for y, then you can't. So implicit differentiation is actually going to be your friend there. Another case is if it's difficult to solve for y. In some cases, just solving for y, yeah, you might be able to do it, but it's going to be really hard to do it. So why not just do implicit differentiation right off the bat? Your last case is that if you just don't want to solve for y, and that's actually the example that we just did. So here in this case, I look at that and I don't want to solve that for y, because when I do solve it for y, I get something really ugly. And I don't want to take a derivative of this. I mean, I was able to do that quickly in my head, but like, I don't want to do all this work for taking that derivative. I don't want to have to do power rule and chain rule and all that stuff. I'd much rather just do this work and just have this sort of weird notation, but just it's a lot shorter of an amount of work. And so those are our examples. Those are our cases of like why we want to use implicit differentiation. Basically, it's just when you don't feel like solving for y, or if you can't, then you have to use implicit differentiation to find the derivative. So then there's also downfalls to this, though. There's really one downfall to implicit differentiation. And that downfall is that your derivative is in terms of y. And so that's really it. I emphasize it a lot because it really is a sort of a big, not a no-no, but it's a big what's the word? It's just something that's weird. It doesn't really make much sense. I mean, let's go back and look at this example that we saw. We have y prime. So we have the derivative of y is equal to 6 minus 2x over 3y squared. Well, the thing is, in none of this work actually tells us what y actually is. And so we're saying that the derivative is equal to 6 minus 2x over 3y squared. I don't even know what y is. And so, because we haven't actually solved for it. I mean, now, what you could do is you could take this, solve it for y, get this guy right here, and then you could just plug it into there. That's fine. But as it stands right now, we don't even know what y is, and we're writing our derivative in terms of it. And that can be bad for obvious reasons. I mean, if you don't know what y is, and then you're saying, hey, the derivative is here, it's pretty much that we don't know what the derivative is yet, unless we knew what y was. And so that's a big downfall to implicit differentiation. The nice thing is that, honestly, we kind of don't care. A lot of the times we just kind of have this as our answer. And we're just like, say, hey, good, we're done. Like, this is fine. We'll just leave it like this. Yeah, it's in terms of x and y, but whatever, that's fine. So that's the downfalls to implicit differentiation, just that your derivative is in terms of y. Let's go ahead and do another example here. Xy plus 4y squared is equal to 10. Now, if I look at this, I could, like I said before, I could start by trying to solve this for y, and I'm gonna just rewrite this a little bit. And I look at this and I'm like, hey, there's a y squared, there's a y, and there's a constant term right there. So I guess technically I could do Pythagoras, or not, excuse me, I could do the quadratic formula. Okay, so y is equal to negative b plus or minus the square root of b squared minus 4ac, which ends up being 160, negative 160. So there's that, all over 8. I mean, I'm doing the quadratic formula quickly there. I don't want to take a derivative of this. That's ugly. I mean, there's a plus or minus, there's a square root, there's an x squared in there. There's just all sorts of stuff with this that just screams, don't take a derivative of this. This is just ugly. And so it's going to be a lot easier to actually do the derivative implicitly. Just take the derivative at this stage right here. And so we're gonna skip all this work. We're not going to bother with that. Let's just take the derivative using our methods of implicit differentiation. And here's what we want to be careful about. Like I've said before, y is a function of x. So when I have x multiplied by y, when I have this multiplication right here, this is two functions of x being multiplied by each other. That screams product rule. So we have to do the product rule here. Let's go ahead and put that in a different color. So I'm going to do my work in blue. So we have to do the product rule here. And so when I do the product rule, I am going to I'm going to now take the derivative of xy. And so actually, let's go ahead and emphasize that product rule on xy. There we go. So I'm doing the product rule on x times y. So what I'm going to do is I'm going to leave the x, and then I'm going to take a derivative of y. And don't overthink this. The derivative of y is the derivative of y. It's just y prime. That's what the derivative of y is. I add to that, I take the derivative of x, and I multiply it by y. I just leave that y as it is. Then I have my 4y squared that I'm going to do my normal power rule derivative on. I'm going to drop that 2 down, multiply it by the 4 to give me 8. Y, and then I have 2 minus 1, which is just 1, so we don't bother writing it. But don't forget chain rule. Remember, this y is a function of x. It's really just a whole bunch of x in there. And so I have to do my chain rule, which says I have to multiply this guy by y prime. And then lastly, the derivative of 10 is just 0 right here. So that's nice and easy. Now, like we did before, we're trying to find the derivative. And what I notice here is I have a y prime in two different places, in two different terms here. And so what I'm actually going to do is I'm going to take every term that has a y prime in it, and I'm going to leave it on the left-hand side of the equation. And I'm going to take every term that does not have a y prime in it, and I'm going to move it to the right side of the equation. You want to be very careful here. This is the only term that does not have a y prime in it. These underlined terms are all together because they're multiplied. So I have to leave them as they are. So I'm going to have xy prime plus 8y y prime is equal to negative y. And you'll notice here 1 times y is just y. So I'm just simplifying that right there. That right there is the same as that. Negative, obviously, because I've subtracted it over to that side. So we've got all that. That's good. Now, what you'll notice here is I have only terms with a y prime on this side. So let's factor out a y prime. I'm going to x plus 8y times y prime equals negative y. Notice that I write my y prime on the right-hand side here. The reason I do that is because if I write y prime of or y prime multiplied by x plus 8y, sometimes this can be mistaken for function notation. It looks kind of like I'm saying, hey, y prime of something. So I always like to be careful. I like to write my y prime on the right-hand side over here. You don't have to, but just pointing that out, just an added step of caution. So we're basically done. Just divide by x plus 8y. I get negative y over x plus 8y. And that is our answer. We have our derivative. And obviously, as I've said before, this is in terms of y, which is bad because we don't actually know exactly what y is, but that's fine. We tend to just leave it here. If you wanted to, if it's even possible, you're welcome to do all of this work right here to get an explicit formula for y, and then take this right here that I'm boxing and plug it into this. I don't expect you to do that. This is totally fine. It's perfectly acceptable in the math community. That's your final answer, and that's good to go right there. The second to last thing I'll say is that if possible, simplify an equation that I give you here. So this might be a kind of a stupid example, but let's say I gave you something that was like, hey, 3xy plus, oh, maybe this isn't that stupid of an example, plus 3y squared equals 8y cubed. Well, what I notice here is that if I factor out a y from everything, ooh, and again, let's heed my advice from earlier. Let's factor out that y over here. You'll notice that I have some cancellation that goes right there. And so then this simplifies down a lot simpler to just that. And so that's just kind of that's a simple example there. You know, if I give you a formula right off the bat, let's go ahead and box that to indicate that that's what I'm starting with here. If I give you a formula like that and you can do some simplification to it, do so, because it's a lot easier to take a derivative here than it is to take a derivative up here. This is just a much simpler equation there. So be careful there. Just as a recap, let's go skip all that work. We already did that. So just our steps for implicit differentiation. We're going to start off by taking a derivative, and you're never going to forget that chain rule term y prime when it applies. Don't get sort of trigger happy and just put y prime everywhere, right? The y prime it pops into place when you're using the chain rule. So you got to keep in mind when is the chain rule applying here, and you have y primes there. Take every term with a y prime and put it on one side. I like to put it on the left side. Move all of the terms that don't have a y prime to the right side. Then you're going to factor out that y prime that's on that left side, on that side that you've moved all of the terms to. You're going to factor out that y prime. And like I said, I like to write that as the factored stuff and then y prime. You don't have to, but I like to do that. Then you're just going to divide, and at that point you've solved for y prime. Do any simplification if you can, and then double check if you can simplify, and then even triple check, because I guarantee you there will be cases where you can simplify it down a lot. So for just for example here, maybe you start off, you know, you have all your work and you end up with, hey, y prime is equal to let's say 6x over 3x plus 2xy. Well, what I notice here is there's an x everywhere. Actually, let me explicitly write that. I could simplify this by factoring first. I could factor out an x. And now look, I have cancellation right there. And so this just is 6 over 3 plus 2y, and that's a lot simpler. So that's kind of what I'm getting at. Simplification in terms of that sense. And then also simplification by looking at the original equation as well. That's going to be important. So you could actually use the original equation to simplify. And yeah, I'll go ahead and leave it at that. That's our steps for implicit differentiation, and that'll be it for the lecture.